Hello, good afternoon, or good morning, good night, good evening to everybody. And microphone is active, so let us go to the lecture of today. And the object of the lecture of today is just a proof of Green's theorem, but not a true mathematical proof. Instead of that, I will give you a formal proof. Formal in mathematical language means informal, which means that it is not a rigorous complete proof. For two reasons, I won't give you the rigorous mathematical proof that you can find in serious books of mathematics. The first reason is that it is very technical. It is quite complicated. I should preliminarily define mathematical objects that are not needed in this course, that are a bit beyond the spirit of this course. Second, the formal proof is a sort of black box. You end up with the result, and if you are not very smart in mathematical sense, then you don't understand why it works. On the other hand, a formal proof, so an informal proof, can give you the right hint for which this strange Green theorem work, and perhaps you can run the risk of understanding what is the meaning of Green's theorem. And I want to communicate it to you. I know you are engineers, you are not going to be mathematicians, so giving a proof of something perhaps for you sounds somewhat exaggerated. Partly I agree with that, but in this case, Green's theorem is so important, and it is so strange, because it is an inequality between two integrals that apparently have nothing to do with each other, that I want to try to explain you why it works, okay? So call it comment, remark, or formal proof as you want. But I think this can be useful to you too, okay? I recall you the content of Green's theorem, and so first step is to define a region D. Region D is a region which is regular, where regular means that the boundary is a closed curve such that at every point of the curve there is a tangent. Okay, here there is a tangent, so it has no corner. Indeed, we could allow corners, but however, in the plain, cleanest version of Green's theorem, we have regularity. Okay? Of course, there can be holes. I want to stress that Green's theorem is bidimensional. It applies to two-dimensional domains. We are in the plane. We are not in the space. In the space, we will have Stokes' theorem. Okay? So, the content of Green's theorem is the following. It says, let D be a region of the plane with the regular properties I recalled before, and C, the curve, be its boundary. That will be a regular closed curve and positively oriented. So always recall that. What does positively oriented means? It means that at every point, if you are going in the positive direction, and not on the other direction, the negative one, the positive direction is the one such that if you are here on bike and you just put your left hand side a bit outside, okay, you drive only with the right, okay, and you keep the left hand side a bit at your side. This left hand side falls into the internal part of the curve. Okay? The closed curve splits the space into an internal part and an external part. And the positive direction is the direction in which the internal part is always at your left hand side. This means if the curve has no holes, this means that you are running on this curve in the counterclockwise sense. Vice versa, if it has some holes, around the holes you are going in the clockwise sense, because here think always of your left hand side in order to fall inside the region, the internal region of the curve, since this delimitates not the region but a hole in the region, then you have to move here clockwise. So clockwise here and anti-counterclockwise here. Okay, this is positive. So this is a preliminary hypothesis, and now the main character of Green's theorem is a vector field, a two-dimensional vector field, F1, F2, and it is regular in the sense that the components of the field are differentiable at every point of D, of the internal region, and then you have continuous derivatives. This can be explained in mathematical terms by saying that F is in C1 of D. Okay? The two components are differentiable functions in both variables, and all partial derivatives are continuous function of D. Partial derivatives, of course, are four. There are two partial derivatives of f1 with respect to x and with respect to y, and two partial derivatives of f2 with respect to x and with respect to y. Okay? Now, this is the long hypothesis, quite long but somewhat natural. Nothing strange is required here. You have to remember what is positively oriented, and all the rest is regularity. So, and this is the formula, the nice, unexpected, and important identity established by Green's theorem. The circulation of the field on the curve, which is the boundary of the region we are considering, and it can be a curve in simple cases, but in other cases it is not just a curve, a closed curve, but more than one closed curve, like in the case of holes. Okay? C is all the boundary. In this case, C is the union of C1, this external part, and C2, the internal part. So, the circulation of F on the boundary C is equal to the two-dimensional to the surface integral on the region D, internal to the curve C, of this strange non-diagonal combination of partial derivatives. You have the derivative of the second component of the field with respect to the first variable, minus the derivative of the first component of the field with respect to the second variable. Okay, this is the identity. We noticed already then this expression, which looks quite strange, is nothing but the z component of the curl of a three-dimensional vector field. This is very important, okay? Because this is the basis, the conceptual basis of the generalization of this result of Green's theorem to the case of Stokes' theorem that you will use a lot in electromagnetism in analysis too. Okay, so this is the identity, and we showed by an exercise how to use this identity. So you have the identity of two integrals, and in the case given by the exercise, the first integral was horrible. Okay, you had to compute this circulation and you ended up with this expression. This expression looks really awful. However, it is not so bad because you can compute it. Even this guy here you can compute because the cosine is the derivative of the sine, so you can do it. However, it is quite long and it is cumbersome, so there are it is quite likely that you miss something and you end up with a wrong result. So I left it as a homework because I was scared of doing that, and it was very likely that I made horrible mistakes. So by using the Green's theorem, the computation is very easy because this component, third component of the curl is just a constant number, -4, and then you ended up with a result. Okay? And now I want to give you this sort of formal proof of Green's theorem, and we start by, by the problem of computing the circulation of a planar field F in the two components F1, F2 on the regular circuit C, this one. What does regular means? It means that it possesses a tangent at every point. So there are no corners here. And it is to be added here that the circuit C must be not only regular but also positively oriented. If it is not positively oriented, just change the sign. It is not a tragedy, okay? But you have to specify. So this is positively oriented. So this is a sort of picture. And now, what I organized here, you can see it, is a grid. I just drew a certain number of horizontal lines and also some vertical lines. So I obtained a grid that partitions the region D, what I always called the region D, which is the region inside the curve C. Okay? Now, what I want to do is the following. I want to consider the sum of all circulations of the field F on all circuits generated by the grid. So first let me put an arrow on F. And what do I mean by that? I mean that I consider the circulation, for instance, on this guy here. This is a circulation, and then another circulation here. Always through positively oriented curve. So I look here, you look at, for instance, I took these two circuits and notice that this circuit here has a side in common with the circuit here. So when I do the circulation of F on these two circuits, there is a contribution which is counted twice, and it is exactly the contribution of this side. But is it really true that it is counted twice? Notice that if I always use positively oriented circuit, once I run through this side on this direction, from left to the right, when I'm doing the circulation here I go, from right to the left. And the other time, when doing the other circulation on the other circuit, I run the same side from left to right. So in the opposite direction with respect to before. This means that these two contributions cancel each other. Okay? And if you think of it just some minutes, you immediately see that this sort of magic always happens whenever you have a side which is common between two circuits. Here, for instance, I did it here. This green circuit. This green circuit has a side here which is common with the lower circuit, the blue one, and it is run through 2 times in opposite direction. The other side here is in common with another circuit here, and it is run through in 2 opposite directions. So think a bit of it, and what you discover at the end is that all internal sides, which means all sides obtained by inserting these vertical and horizontal lines, gives no contribution to the circulation because it cancels. This guy here cancels when I do the circulation here. So the only sides that give a contribution are the sides lying on the curve, because they are run through only once. For instance, this side here is run through only when I do the circulation here. Because I don't do the circulation here, I remain inside the curve. Okay? This is very nice. So, I can write this equality. The circulation of F on C is nothing but the sum of all circulations of F on all CIs, where the CIs are the circuit line in the interior, always in the internal part of the curve, and are obtained by the construction of the grid. What I wrote here is just what I did now. And so you have to catch this fact, grasp it. Okay? The circulation on C is the sum of all circulation here. All circulations here. And now the step is compute what is the contribution of a rectangle like that to the circulation. Of course, the final contribution is 0, because every side here is cancelled by a neighbor circuit. But this is not the point. I want to focus on it, on a square like that, and see what happens. So first, let me introduce some notation. Okay? First, this is a circuit CI inside the curve C, and let me give some names to points. The left downward corner corresponds to the point XY in the plane. Then we move here horizontally for a length delta x, so we got to the point x plus delta xy. Then we move upwards up to the point whose coordinates are x plus delta x, y plus delta y. Then we go leftwards and we get the point x, y plus delta y, and then finally downwards we go back to the starting point xy. This is the circuit, very simple, 2 horizontal and 2 vertical sides. But let me be precise. Being precise here means specify precisely how do we run through these sides. So write down a parametrization of the curve. It is a stupid curve. Of course, notice that there are corners, but they don't count. We can apply Green's theorem too. Okay, so we have a very easy parametrization of this side, which is r of t has a y variable which is fixed on y. We start from y, we arrive on y. And the x variable is moving. So the x variable will be x plus t, with t running from 0, t equal to 0 we are here, up to x plus delta x. For t equal to delta x we are here. So what we got here is a uniform motion on this side with a constant velocity 1, 0. Constant speed 1, 0. Okay? So if you understood this point, the others are made exactly in the same way. Second side, we go from x plus delta xy up to x plus delta x, y plus delta y. So the x variable does not move, and so I did not write here precisely the parameterization, it is exactly like that, but what we are moving is y. So we had a velocity here which is r dot is 0, 1. Okay, I can write also the, here we have r of t, that in the second side is fixed on x plus delta x on the first variable, while the second variable is y plus t, and t runs through the interval 0 delta y. So at t equal to 0 we have that the second variable is exactly y, and at t equal to delta y we have that the second variable is y plus delta y. So we are at the final point of this side. And again the velocity is constant and it is 0, 1, velocity 1 along the vertical axis. So what is a bit different, but not so much different, is the third side, from here, then leftwards here at the third corner. And again, what is fixed here is y, is the y variable, y plus delta y, and we arrive at y plus delta y. So in our parameterization, here we have y plus delta y, and the first variable, the x coordinate, can be written as x plus delta x minus t. Minus t because we are going backwards in the x variable. The x variable points rightwards, but we are going leftwards. So I have to put here minus t, and t lives in the interval 0 delta x, in such a way that for t equal to 0 we are at x plus delta x here, and for t equal to delta x here we are at x plus delta x minus delta x, so we are at x here. And of course the velocity is r dot is equal to minus 1, 0. And when we go downwards here, okay, I don't spend time, we do a very similar parameterization, and r dot is equal to 0 minus 1. I stop here because we are more or less at the limit length in order to upload it safely on YouTube or other servers, so I come immediately.